No, thanks, Karen. And yeah, thanks for the invitation to speak here. Also, it's very nice to see my old office in the background of Karen's screen. Makes me feel at home. Okay, so I'm really excited to tell you all about this project. It's very much still ongoing work, started this summer. But yeah, let's get into it. Let's see. The setup's something quite familiar, but we'll go through it anyway. So we're gonna just so far this project's only in type A, that we'd like to extend it someday. So we'll have a orientation of an AN Dynkin diagram, and we'll pick an n vector of non-negative integers. So you can see I have some running examples along in the purple. And then you will think about the set or variety of all representations of the quiver with that dimension vector, which is just like k to some just a really simple vector space, right? Because you're just picking any entries in all the matrices that you have where the sizes are determined by D. So for example, yeah, in this running example, any possible representation that looks like this on the right. And we know some of these will be related simply by some change of basis formulas, and that's governed by this GD, this product of general linear groups. And from Gabriel's theorem, we know about the indecomposables in type A. They're quite easy to explain. And we also know they're in this really natural bijection with positive type A roots. So I'm writing alphas since it's somewhat common to write a single alpha as the simple root in a root system. So you can see the indecomposables are the IPQs, and the positive roots are alpha P plus up to alpha Q. All right. And from Carl-Schmitt properties, we know that this space decomposes into orbits of direct sums of indecomposables. And of course, what indecomposables you put together, there's some natural arithmetic rule. You have to be able to add up their dimension vectors and get your original vector D back. Okay, nothing surprising. The thing about this project, we were in a group at a research workshop looking at Kostant partitions. And the point is this problem where you take a random vector and then write it as a positive integral combination of positive roots. So it's sort of like doing a partition of integers, but now you're doing it with vectors. And your vectors you start with are positive roots of some Lie algebra, here just type A. That's called a Kostant partition. And people in algebraic combinatorics like studying Kostant partitions. From the name, Kostant used these to define a weight multiplicity formula for Lie algebras. And so understanding them had some benefit to them. And for us, it just naturally shows up if you want to think about such a space. And thinking about this from either perspective is certainly not new. So from more of the quiver representation side, like most of us are from, there are many authors, so I have many in parentheses, and there's many more. What's more common and a little better to study is studying the closures of these orbits. So then they're not all disjoint. And those are at least sometimes called quiver varieties. So I picked up that name for this talk. So the quiver varieties are the closures of these orbits. Okay, now on the algebraic combinatoric side, a few years ago, Benedetti, Hanusa, Harris, Morales, and Simpson showed a connection between Kostant partitions and here's the juggling magic, multiplex magic juggling sequences. So really it's a bijection when you specify which set of juggling sequences you want to look at. Okay, so mathematically, there's a few ways that you could talk about juggling mathematically. The main premises you need are that throws and catches, so you're throwing and catching balls. Throws and catches have to happen at discrete times. And you also think about a throw happening immediately. That doesn't take up any time. So from the ball landing in your hand to going back up, that can all happen at your like one discrete time step, which is why I've drawn very steep lines going up in this picture. And these are multiplex juggling sequences because sometimes you throw more than one ball. And they're magic juggling sequences because you can see the blue one we have to have it kind of leave the system to make sense. In the original paper, there's like anti-balls that cancel with balls. But to make the correspondence work, we have multiplex magic juggling. Though for certain choices of D, you would just recover some more ordinary juggling. Okay, so then that's juggling. And then this picture is implying how you could go from a Kostant partition to either a juggling sequence or the closure of an orbit. So for the juggling sequence, each positive root that appears gives you a throw, where the smallest index tells you when you throw. And if you add one to the biggest index, that's when you land. So very natural. Okay, and then going to the right, well, first, if you just think about taking the direct sum of those indecomposables, you'd get a bunch of representations where the ranks have equality here. And then to take the closure, we just get the inequality. So now we have a new combinatorial object to index these quiver varieties, the juggling sequences. And we were, of course, in type A, there are many combinatorial objects already we can use to describe things, but something that excites us about the juggling sequences is places they've appeared in math otherwise. So in the non-multiplex case, when you have this, you only catch and throw up to one ball at a time, juggling sequences have appeared to index positroid varieties. These give a nice stratification of the Grassmannian. So this is a quick illustrative example of the idea. So here I have an ordinary juggling sequence. So now I've expressed it a bit differently. Just below every ball, I've written the height of the throw, which is how many beats until the ball lands again. So here, and it's a periodic sequence. So for example, you could take the representative 3, 1, 2, 2. And the point of this indexing is you associate this with all points in GER 2, 4. There's a way to find out that it should be 2, 4 in this case, but in GER 2, 4, where, for example, V1, because throw 1 was 3, V1 has to be in the span of the next 3 vectors. And what I'm implying when I write that is it's not in the span of the next 2 vectors. So that's like the minimal number. Anyway, so a future thing for what we would like to do is what will multiplex juggling give us in this setting? Like, does this still give us some sort of nice subsets of the Grassmannian or some other space? And then, of course, then you can naturally link that back to the Quiver's representation. So anyway, this remark is about things we'd like to do, and then I can tell you about things we have done. The first thing we did was calculate formulas for the codimensions of these quiver varieties. So that's, of course, in terms of the juggling, and yeah, in terms of juggling, but also you do need to take into account the orientation of the quiver. So the Kostant partitions, they don't care about the orientation, right? That's just how can you add up these vectors to get this one vector? But the codimension really does depend on the quiver. So it's easy. Everything's easiest in the linear orientation, which is also where a lot of papers focus. In the linear orientation, this formula is very nice. It's just the number of throws plus the number of like balls that collide. So when you draw it in a planar way and you see them cross, you add all those up and that gives you codimension. So the biggest ones have minimal throws, minimal colliding in the linear case. Next, looking especially there were a series of papers by Abiyasis and Delfra, and something they like to focus on was studying the lattice of these quiver varieties. So you can study it under inclusion, and you can also describe what that lattice, like what cover relations mean in terms of the defining representation, like the direct sum of indecomposables that would correspond to not just the closure, but the ordinary thing. So they have a bunch of ways to describe these lattices, basically. And we can describe it in terms of juggling and show that we're getting the same lattice. And then what is quite fun is to take these lattices of juggling, which again, different orientations, the juggling sequences have different codimensions, so they move around in the lattice. But you seem to get always the same lattice. And so we have a conjectural dimension preserving bijection between varieties for 2 different orientations. So I'll show you an example where it's small enough to say some things. Let's see. So, okay, so for our running example 1, 2, 2, 1, and both the linear orientation, which where I said, yeah, bigger things have fewer throws and no crossings, and then a non-linear orientation where things are a little different. So you can see we have the same shapes, and I've drawn these really to imply this map. Oh, sorry, I should say we've restricted to only like kind of the top of the lattice, where you have 2 or 3 throws, 2 or 3 summands. Otherwise it'd be too big. But so for example, they each have this maximal element, but it looks different between the 2. So we should send the G on the left to the F on the right and so on. But it was a lot of fun stuff we are still planning to work on. And yeah, we're hoping that juggling sequences can take off as a something that Quiver people think about too. Anyway, thank you.